Hello, Dr. Ko. My name is Shazeb Ahmed, and this is homework 1. In this video, I'll be explaining the variance in air pressure and temperature with altitude. So we're going to assume that it's in isentropic atmosphere, which essentially means that the process is adiabatic and it's also reversible. So we're going to start out with the law of statistics. So the law of statistics is dP over dz equals negative rho g. And then we're going to use the ideal gas law and change up the equation to dP over dz equals negative mp over RT times G. So M is the molar mass and P is the temperature. So we're doing this to get the density. So now we're gonna rearrange the equation to keep the constants on one side and pressure and temperature on another. So we're just gonna do this. So it's gonna become T over P dP equals negative M over R times G times dz. So next we're gonna integrate both sides. So it'll become, integrate here, P1 to P2, and also integrate here, and this is gonna be Z1 to Z2. So we can solve out the right side pretty quickly, and it's just gonna go to this, keep the left side as it is, P1 to P2, T over P dP, and when we integrate the right side, we get negative mg delta z, which is the change in altitude all over r. So now we're going to use this to find the pressure equation, this equation right here. So in order to get the temperature equation, we use dV equals change in Q minus P dV. And since the process is adiabatic, there's no heat energy. So this value right here will just become 0. And it becomes dV equals 0 minus P dV. So using the ideal gas law, PV equals nRT, the equation becomes dV equals negative RT over V dV, which can be transformed to this equation. Cu dt equals negative RT over V dV. So then we're going to take the integrals of both sides. So this becomes T1 to T2, and this becomes V1 to V2. So using logs, we get this equation, which is Cu ln over T2 over T1 equals negative R ln, we just pull out the constants, over V2 over V1. So we're going to be using this equation to solve for the temperature and to get the pressure equation. And I'm going to clean up the board right now, and I'll be right back. All right, I'm back. So last section of the video, we logged both sides, so we can actually rearrange that equation to just ln T2 over T1 is equal to ln V2 over V1. And we can just take the constants that are in front of it and we can just put it in the exponent. That's some algebra, so I'm not going to explain that. And when you take the log of that, that equals t over t1 equals v over v1 raised to the negative r divided by cv. We can rearrange that equation as well. T over T1 is equal to RT over P over RT over P1. And we just did that using the ideal gas law, PV equals nRT, and it's still raised to the same exponent, which is just negative R over CV. So the pressure, the RTs are going to cancel each other out. The R's are, because we're solving for temperature and pressure. So equation just becomes T over T1 equal to T over T1 times P1 over P. All raised to the negative R CV. Can then rearrange that equation to T over T1 R over CV plus 1 and equals P over P1 over P over CV. So next step, the R over CV plus 1, which is right here in this exponent, it can just becomes CP over CV equals gamma, and we can rewrite the equation in terms of gamma, and we can just get T over T1 is equal to P over P1 raised to the gamma minus 1 over gamma. Rearrange the equation one more time. Just skipping through the algebra steps. So this just becomes T equals T1 times P over P1, all raised to the gamma minus 1 over gamma. So now we're gonna substitute this equation substitute this temperature equation into the first equation we solved in the first step to solve for temperature. For pressure. So we had integral of P1 to P2, T1 P slash P1 raised to the gamma minus 1 over gamma all over P dP equals negative mg delta z all over RT. Sorry, I think this is minus here, and this just equals T1 over P1 all over gamma minus 1 all over gamma. Sorry, I think I'm gonna correct myself here. What am I thinking? dp is equal to negative mg delta z, change in altitude over r, my mistake. So now we just pull out the constant temperature and the pressure, and it can lead us to this next equation, which is T1 times P1 raised, T1 times P1 raised to the gamma minus 1 over gamma integral of P1, P2, P raised to the gamma minus 1 over gamma dp, which equals to negative mg delta z, which we got earlier. So now we're gonna move the constants to get the integral all by itself so we can solve for it. And I believe in this step we would just be equal negative mg delta z over r times T1 times P1 gamma minus 1 over gamma is equal to integral of P1 to P2 P raised to the gamma minus 1 over gamma, and then subtract 1 from that dp. So this integral equals to P gamma minus 1 over G over gamma minus 1 over G P1 to P2. And then that equals P2 gamma minus 1 over gamma minus P1 raised to the gamma minus 1 over gamma. This is just raised. I just ran out of space a little bit. And all over gamma minus 1 over gamma, which we can then simplify to P2 gamma minus 1 over gamma minus P1 gamma minus 1 over gamma, which is equal to negative mg delta z over RT 1. And then we multiply this by P raised to the gamma minus 1 all over gamma. And we multiply that by gamma minus 1 over gamma. So I'm running out of room here, so I'm going to clean up the board, and we just have a few more steps left to finish the problem. All right, so we're on our final stretch here in this part of the video. I'm going to finish solving for the pressure equation and also the temperature equation. So from that last equation we got from the last video, with combined like terms, we can get combining terms. We get P2 raised to the gamma minus 1 over gamma equals P1 raised to the gamma minus 1 over gamma Then we multiply this whole thing by 1 minus, put that in parentheses, mg delta z over RT, RT1, and then we multiply that by gamma minus 1 over gamma. So therefore, our temperature would be this. Let's just solve for the temperature equation. P2 is equal to P1 times 1 minus mg delta z RT1 times gamma minus 1 over gamma times, we're going to move this term here back down here. We're going to divide it over, so it just flips sides. It becomes gamma over gamma minus 1. And there we have it. That's our pressure equation that we were solving for. So now since this is the final pressure and only Z is changing and everything else is constant, we can use this temperature equation to get the temperature equation that we're looking for when altitude differs. So this is the equation we're going to use that we got earlier. T equals T1 multiplied by P over P1, all raised to the gamma minus 1 over gamma. And using this equation, we get T equals, we can substitute the P in for this equation that we solved just now. And we get T equals T1, we're going to put this in brackets, 1 minus mg delta z over RT1 times gamma minus 1 over gamma. And there we have it. That's going to be our temperature equation. So this, when you multiply by this, just equals 1. So everything just, I believe everything cancels out. Yep. So that's why this will be our final temperature equation. All right. Thank you for watching.